Hi guys, we have analyzed and redesigned a 3D printer for this semester. There are many types of 3D printers, but we are specifically analyzing a fused filament fabrication printer where various types of materials, including plastics, are melted layer by layer to create a 3D object. 3D printers are used by hobbyists and industry professionals to manufacture products with small batch sizes, design prototyping, and to manufacture complicated parts. We chose to analyze a simpler and cheaper 3D printer that uses T-slots with rollers to move in the X, Y, and Z axis. Due to complexity, we are focusing our analysis on the X-axis subassembly pictured on the right of the screen. This is our product's Explorer guide view.
For the fast analysis, we changed a few of the wordings for each of these parts to better specify what we're going after with each of these breakdowns. As you can see in the functional component mapping matrix, the actual functions have stayed relatively the same for each of the parts. However, changing these titles has further made it obvious what their performance and their role in our part is for. The quad chart classification has been adjusted to more fit a classical quad chart setup, and the fan cover has moved from keep as is to redesign with DfMA. A lot of the keep as is parts are purchased components and therefore cannot be easily changed during our DfMA, and the DfMA parts have been selected as primarily functional or structural components, which are more easily and more readily redesignable by us.
So most functions from the FAST are the same for both the primary and secondary groups, except for melting material, vibration removal, and maintain accurate part geometry. And all the parts that correlate with the customer group functions are listed on this slide, with the T-slot frame, hot end, bed leveling sensor, and fan cover being modular. And here are all the visuals for the modules. Note that the bed leveling sensor is only added to the secondary assembly and is not included in the primary. And it's the main reason why the maintain accurate part geometry FAST function is different for both groups. On this slide, you can see how the module interfaces that include the hot end mount, X-axis mount, and Z-stand. The Z-stand and X-axis mount fasten both the primary and secondary T-slots to the Z-axis T-slots and allow for stability while moving, while the hot end mount accommodates for primary and secondary hot end setups.
The primary design was analyzed for manual assembly, as shown on the left chart. Final numbers for labor cost and total operating time are given, as well as highlighting the two parts in this chart that we just chose for redesign. The next one. Many of the parts here are actually fasteners, which could be eliminated and do not count towards total minimum number of parts. And many of these have to do with the V-rollers. The final assembly time is 741 seconds with a total minimum part count of 32 and a total efficiency of 12.9%. The two parts picked for redesign are the limit switch bracket and the fan housing. The limit switch bracket was given slopes to enhance its asymmetry to allow for better placement during assembly. The limit switch was moved to the top surface as opposed to underneath, which allows for a hand tool access. And the M3 screws were shortened to use the more standard screws used everywhere else in the design, which will help reduce the total part count or the total variation of parts. The fan housing itself was completely eliminated of fasteners, which prediction of fasteners. Toolless assembly allows for snap fits, and these slots are designed to fit seamlessly onto the hot end mount and seat properly when completely assembled, which should increase and allow for easier assembly time. The parts given in green are improvements and the elimination of the M3, two types of M3 screws. The total time now is 704 seconds with a total efficiency of 13.6%. The redesigned limit switch bracket still uses the screws because it interfaces with the motor, so they cannot be completely eliminated. And the fan housing is slightly larger to accommodate the snaps. However, the elimination of the screws should help cover the additional material cost.
So we chose to analyze the Z-stand subassembly for design for automated assembly due to possible utilization of feeding, orientating, and insertion, as well as the classification made in the quad chart. These parts are platforms to allow for the T-slot module to be assembled for both the primary and secondary arrangement. And the total automated assembly price came out to be $13.71. And most of the cost was due to its high handling and insertion cost, primarily because of the non-vertical assembly. And on this slide, you can see the exploded views for both the before and after redesign. We followed design for automated assembly guidelines 1, 2, 5, 7, and 12. So we added flanges to facilitate orientation, as well as to deter overlap during feeding. And we also removed most or a lot of screws that were unnecessary. And now all the fasteners are on one side, so Z assembly is made possible. In this slide, you can see the more detailed breakdown of the analysis with the total part cost coming to $7 or $6.10.
Right. So for the first part, we redesigned the Z-stand with reference to the function component mapping matrix, the part that was crucial to maintain part geometry of the whole system. The most critical dimensions were the diameter of the holes and the thickness of the Z-stand. We picked steel as a material with flatter folded sheet with a mass of 128.11 grams, section thickness of 23.94 mm, and a tolerance of 0.1 mm, and roughness of 1 micrometer with a batch size of 10,000 units. The recommended process of making this part was sheet metal working. The second part that was redesigned was the limit switch bracket with reference to the function component mapping matrix. The bracket is essential to give tool access to the limit switch and make it secure. The most important dimensions were the thickness of the slopes, the thickness of the whole system, and the diameter of the holes. We picked ABS as a material with the shape of a modified prismatic non-circular part with a mass of 4.02 grams with a tolerance of 0.1 mm, section thickness of 19 mm, and roughness of 1 micrometer, and batch size of 10,000 units. The recommended process was injection molding.
So for the injection molding designed for manufacturing analysis, we chose the X limit switch, which before was housing the X limit switch inside, which required expensive ribbing and bosses. The total manufacturing cost came out to be $5.11 because of that. So utilizing DfM 1, 2, 4, 6, 7, and 8, we redesigned as explained before, which totaled to $1.48. For the sheet metal, we chose the Z-stent to redesign, and before the cost came out to be 62 cents. And utilizing DfSM 5, 6, 7, 8, and 11, we redesigned the part, and which resulted in slight increase in price that totals to 72 cents. And after submitting a Hubs quote and extrapolating price for 10,000 units, we noticed an average of 70% difference in price when compared to the analytical method. And this is because when doing the analytical method, we simplified the geometry of the part to more easily find the area, which directly impacted the cost.
So for the design of product server system, we suggest a cloud printing service that says maintenance after logging certain amount of print failures. It monitors filament levels and provides an easier for replacement, and a customer support button which helps with repair or maintenance. The customer experience benefits with this are it promotes product longevity, it makes printer repair an issue, and it streamlines printer functionality. The environment impact are it promotes printer repair versus replacement. It increases reliability with failure detection and steps to combat. It enhances maintainability and serviceability with an easy customer support, and it integrates product functions.
So the overall redesign of the X-axis assembly was able to achieve a better assembly time and a more streamlined assembly process, a complete parts reduction of several screws, and a cost reduction of $11.14. Additional benefits are better access to critical areas, ease of maintenance, and a modularity allowing for 2 distinct product groups. Disadvantages are that components could have been further simplified. However, this would require an overhaul of almost the entire system as many of the parts interact. And the use of V-rollers should have also been eliminated as they required many parts to put together, but they could not be completely. Different approach would have been to take a much smaller portion of even the X-axis assembly, such as the extruder or the hot end in specific, which would have had fewer parts and would not have had the snowball effect of creating more redesigns. That concludes our presentation.